The last part of this section is not specifically related to the MVT, but is about using symmetry to evaluate definite integrals, okay? And so I want to talk about a couple types of functions. First of all, we have the integral from negative pi to pi of sine x dx. Now, could we actually just do an antiderivative of sine x? Yes, it'd be negative cosine x, and then we could plug in pi and negative pi, but I want to think about what this looks like with a graph, okay? So if we're talking about the graph of sine x, we've got something that looks like this. So here's our negative pi to positive pi, and there's pi over 2, negative pi over 2. And if we're integrating from negative pi to positive pi, we have this area being subtracted, this area being added, and due to the periodic nature of sine, meaning that it is the same shape recurring, okay? We know that those are going to cancel out because they have the same area, and this is area that is subtracted. So we can say, without even evaluating this algebraically, that the integral is going to give us 0. So let's think about another odd function as well, because sine is an odd function. So let's think about something like y equals x cubed, because we know that that's odd. All right, let's think about what the graph is. If we have y equals x cubed from, let's say, negative 2 to positive 2, okay, and we integrate this, we know that the area of this and the area of this are the same, okay, but this one is counted as negative because it is below the x-axis, so the integral from negative 2 to positive 2 of x cubed is going to be equal to 0 as well, okay? And actually this is true for any odd function. As long as a function is odd, then generalized, the integral from any value to its opposite will always be 0. So we could say then the integral from negative a to a of f of x dx is equal to 0. Okay, so that's going to be helpful if we have maybe some complicated odd function and we want to know the integral from, some number to its opposite, then we can quickly say this is going to be equal to 0. Or maybe you just know that f of x is odd, but you're not given an equation for f of x, then we can use this property to still evaluate the integral, okay? Now let's talk about even functions real quick. It's not quite as nice because everything doesn't cancel out. However, so let's think about something like y equals x squared, okay? So y equals x squared looks like this. If we're evaluating from say negative 3 to positive 3, something like that, we know that this area is the same as this area. So that would be the same thing as integrating just from 0 to 3, but then doubling it. All right, and that's going to be true for another even function. Think like cosine. Okay, so cosine looks like this. All right, wherever we go from on the left, so let's say right here, okay, whatever that value is. If we go from, here's negative a, here's positive a, we are going to have twice the integral of from 0 to a, okay? So things aren't canceling out here, but we know that this is the same as this, and this is the same as this, so it's the same as 2 times the integral from 0 to a. So we could say that the integral from negative a to positive a for any even function f of x is equal to twice the integral from 0 to a of f of x dx. Okay, so there's just a little bit about symmetry that can make solving a little bit easier. Okay, and then one more example I want to do is not specifically about 4.5. It's really more of a 4.4 thing, but it's an important one. Okay, the second fundamental theorem in a rearranged order is what is frequently referred to as AP's favorite formula. Okay, and I'll show you what order I mean by that. Okay, AP's favorite formula is capital F of B is equal to capital F of A plus the integral from A to B of lowercase f of x dx. Now, when we did the second fundamental theorem in the 4.4 notes, we said this was equal to capital F of B minus capital F of A. So in other words, this was on the other side, okay? But what they really, really like to ask about is they like to say, what is a future value given an initial value of a function and a rate of change formula, okay? So in this type of situation, we have some unknown later value. Okay, so this is, and actually I'm going to specify amount. Okay, this is some later amount, that's the unknown. This is an original amount. Okay, that's going to be given, and then this is the rate of change of the amount. Okay, so a quick example would be like you're given a position at time 0 and you're given a velocity function, so that's your rate of change of position, and we want to know what is the position 10 seconds later. So we would do the initial position plus the integral from 0 to 10 of the velocity function, and that would give us the position later at 10. So let's do another quick example. So let's say that water leaks out of a bucket at W prime of t, so that's the rate of change of the amount of water, equals negative 20t plus 3 gallons per minute. Okay, and if there are 130 gallons at time, I don't know, 2, how much water is in the bucket at t equals 6 minutes, okay? And I'll be honest, I don't know if this is going to come out to be even, I mean, it might be a negative number, so we don't really care about the final answer. Let's just work on the setup, okay? So instead of writing just the integral and saying that's equal to the antiderivative, so in this case w at b minus w at a, what we're really doing here is we're trying to find the amount of water, because w is an amount function, because this is a rate of change of amount. So W of 6 is the gallons in the bucket at time 6, okay? And that's going to be equal to the gallons in the bucket at time 2 plus the integral from 2 to 6 of W prime of t, which is negative 20t plus 3 dt. Okay? So this is gallons at t equals 6. This is gallons at t equals 2. And this is the rate of change, we'll say in gallons per minute. And so this total expression is the net, well, it's going to be all negative because water is not going to leak back into the bucket. Okay, so this is the net change in gallons over the interval from 2 to 6, okay? And then we would evaluate that to get the final amount.